Hi everyone, welcome to the training of high-strength dynamic test. How we get data with high quality? The first important thing is the hammer weight. We need to make sure we use heavy enough hammer to activate enough soil resistance. So according to the standards like ASTM and other specifications, 1% of the ultimate capacity is the lower limit, and 2% is more recommended. And for drilled shaft with large diameter, we may need bigger hammer weight, say more than 2%. And bigger hammer weight, lower drop height is preferred. That means we'd better to use bigger hammer weight, but with a lower hammer drop height, because this could produce lower stress to avoid breaking the pile head. For hydraulic hammer or diesel hammer, we may require less hammer weight because for hydraulic or diesel hammer, the drop height could be higher. And make sure we use hammer guide. Prepare the site for the guide installation. We need to make sure that the site is flat enough for the guide installation. And make sure the hammer center hits the pile center. Third, make sure the top surface of the pile and bottom surface of the hammer is flat, so we can avoid eccentricity problem. And the fourth, start with small drop height and increase the drop height gradually. Last one, protect concrete pile head in case of breaking the concrete. Usually we use a steel casing to protect the pile head. Here we have some pictures of the testing site. Test without guide may cause damage, and not only damage to the pile, but also could be damage to engineers. So it is not good. And if there's no protection, the pile head could be broken. It is not good. This is the eccentricity problem. We can see big difference between F1 and F2 if we check individual force. Even for F1, it is compression, and for F2, it is already tension. So it's very serious problem. Also this one, F1 and F2, big eccentricity problem. Also this one, very serious problem. And for this one, I think besides the eccentricity problem, we also have the problem of sensor installation, which we will discuss later. If we use a guide properly, the data quality will be better. So check this one, F1 and F2, a very small eccentricity problem, and the proportionality good. Data go to 0 at the end, very good. This one also. This is a diesel hammer. We know that usually diesel hammer or hydraulic hammer, they will produce a better data quality than a free drop hammer. For this is diesel hammer, the proportionality very good, the eccentricity very small, and data go 0 at the end of data. So it's a perfect data. This is some hammer guide we're using. These hammer guides is usually used in China. And also we have some guides from other countries. Another important thing to make sure of good data quality is the pile cushion we use. Usually we use plywood as a pile cushion to lower the impact force on the pile head to avoid the concrete break, and make sure the force is evenly applied on pile head. So usually we recommend using a plywood as a pile cushion with the thickness of 50 to 100 millimeters. The pile cushion, if it's too thin, pile head could be easy to break. But if it's too thick, it will absorb too much energy. It will not easy to activate the soil resistance. And next is the sensor installation. We need to make sure that we install the sensors properly to get a good data quality. Here's some points of the sensor installation. First is the location. Usually, we require to install the sensors 2D below the pile top, at least 1.5D, and where D is the diameter of the pile. And second, the distance between the boreholes for strain gauge is 76 millimeters. The distance between strain gauge and accelerometer is about 50 to 100 millimeters. This is not very strict. Here's the picture of the sensor installation. And here is the sketch of sensor installation from ASTM. This is for pipe pile. This is for concrete square pile. And this is for wooden pile. And the last one is for steel edge pile. The second is the bolts we used to install the sensors. Usually we recommend use good quality bolts, 304316 stainless steel. Bolt's diameter is 6 millimeters, and we need to use a drill head with diameter of 8 millimeters to drill the hole on the pile. When installing the sensors, we make sure to attach the sensors to pile surface tightly, and the sensors should parallel to the axle of the pile. And the wire tail points to the ground, especially for the accelerometers. Actually, for strain sensors, the direction of the wire is it doesn't matter. Here are some examples of the poor installation of the sensors. For this picture, we can see much frequency noise due to the loose of the strain sensor. And this one also, it's bad data quality because the strain sensor is not installed properly. And this one. And we need to make sure the sensors is installed on the hardened concrete so that you can make sure we measure the real strain of the pile. Here are some common problems we're seeing from the data. Here, we can see that the proportionality is not very good. It is because of the wrong input of sensitivity factor of the sensors. That makes the force is much higher than the velocity. And for the proportionality problem, the parameter WS, that is elastic wave speed, will affect the proportionality. Here is the correct wave speed, 3900. We can see that the proportionality is very good. But if we change the wave speed to 3500, we can see that the proportionality is not good now. The force is lower than velocity. And if we change WS to 4500, it's similar to the previous example, which is the wrong input of the sensitivity factor. They all cause the bad proportionality. So from this equation, we can see that the WS, the wave speed, will affect the proportionality. But elastic module E and section area A, they will not affect the proportionality problem. But can we say if the force is higher than velocity, it is definitely bad proportionality? The answer is no. Take this for example. We can see that the force is higher than the velocity, but the proportionality actually is good because we can see from the beginning, the rising point, to here, the force and the velocity, they meet each other well. And after that, they separate. And this is because of shallow soil layer is very hard. So the shallow resistance is very high. We know that the soil resistance will separate force and velocity curve. So the shallow high resistance soil layer will separate F and V, at the peak of the plot. So for this data, the proportionality is good.